right side and the exponent in the left side. So when I send 1 here, what it will tell me? When I send 1 here, what it tells me? On the right side is what? Is the larger exponent. Makes sense? Makes sense, guys? Because we will go to the next steps. This is the one, the exponent that we will not touch, right? This is the exponent that we will not touch, right? That will be the result. Okay, so this is here. Once we determine this is the largest exponent, the result, next step, will have the largest exponent. Okay, so because of that, we passed it as is, okay, here. So if this is the right exponent here, if we send 1, this means that the exponent in the right is the bigger exponent. So because of that, we pass it, we don't touch it. The other one is smaller, so because of that, we did these things on it before, the fraction part. But the result here will have the larger exponent because we didn't touch it. You agree with me? Simple? All right, so this is the idea here. And then the control, so the control will determine, will send a signal here. These signals, what do you think about them? Any relation between them? They are inverse of each other, right? This is 0, definitely this is 1. Right? Because to select which exponent is the smaller exponent, which one, which fraction is for the smaller exponent, and which fraction is for the larger exponent. The larger exponent, the fraction will pass as is. The smaller exponent, we will have this difference to determine how many times we shift it to the right in order to match the exponents. But the largest exponent will pass as is here. And then after that, I will be able to do what? To do the addition or subtraction. Then after that, the control will tell me here to choose what, between what and what. Here, okay, so it selects here, as you can see here. Okay, it selects something. Either this one or this one from the control panel. What is this signal coming from? From the control. Okay, so here will tell me that this is what? After the add, there is a normalization process. Okay, so it will tell me, I get this one, okay, then I will pass in order to shift left and right, because sometimes the normalization, sometimes when I add the fraction, it will be less than the in the right of the binary point. So I might be able to shift it what? To the left during the operation. And sometimes shift it to the right. So this is here happened in the step 3 in the normalization process. What's the increment and decrement? We'll do what? We'll work on what? These ones. Increment and decrement what, do you think? The exponent. We'll increment the exponent, right? When we do the normalization, either sometimes I shift it to the right or left, and then I decrement or increment the exponent that I got it from here. Okay, so because of that, this is what's going to happen. And then, of course, this process will have feedback, continue with the rounding at the end. But the most important that I need you to understand until this step at least, everything here. So you should track or trace the signals here. So you'll tell me, okay, this is here the exponent in the left, this is the exponent in the right. If I give you the actual exponent, then you will figure out what's the exponent that will pass here, and what's the shifts that will be passed here, what's the shift amount, and then which one will be selected here, 0 or 1, and which one will be selected here, 0 or 1, based on the exponents. Okay? You should be able to subtract the exponent and give me the result here, which is exactly the same shift amount to the right. Okay? Makes sense, guys? So these things, you should trace them. Of course, I put them on the homework assignment. I will put you this circuit, and I gave you 2 numbers, fractions, right? Exponent with bias exponents, right? The representation. And then I told you, okay, trace some signal. What is this signal here? What is this signal here? Okay? Remember that these are number of bits. This is exponent. But this is just shift. You can tell me that this is shift 2 or 4 in binary or in decimal. What is this here? You should be determine what is this value. If it is 0 or 1, and this is 1 or 0. Right? You should be able to do that, trace them on the circuit, right? That I provided. Make sense? Yes?
So is that arrow from step 4 to step 3 because you round and normalize?
That's right.
Okay.
You normalize and then you round. After that, sometimes when you round, if there is like here 1, 1, 1, 1, something like that, this bigger number, if you round it, it might give you this one, and again, it will get this one, so you need to normalize again. Make sense? Because sometimes if there is a certain numbers, when you try to round it, it will put something value here. Okay, so because of that, you have to normalize it again to return back to normalize.
What is that situation? Is it
As I mentioned, Imagine this situation with normalization. Suppose that you have 1.99. So you get this result 1.99. If you want to normalize, for example, to the 2 bits, this would be like what? 2.00. Okay, so this is the rounding, but this is not allowed, so you have to normalize back again. Okay, so this is the idea.
Because you only want one.
That's because you want one only.
Yeah.
Right? Because this one here, actually 2, this will be 1, 0, right? Which is not normalized.
Gotcha.
So this is the idea.
Okay.
Any other questions? All right. So this is the just floating point adder, hardware. Floating point multiplication. Okay, so this is the multiplication. So we finish from the addition. Usually the multiplication circuit and the addition circuit, floating points similar to each other, are similar to each other. So it's here, this is here the multiplication. One of the key steps when it comes to the multiplication, you might think about it. What's the annoying step that I don't want to see it now in the multiplication? I see it in the addition, but I don't see it in the multiplication. Annoying step. Which step? That I will not deal with it this time now with the addition. I dealt with it within the addition. Comparing the exponents. You don't add them. Which step that you don't want to include it here? Align. There is no alignment. Right? You don't have to worry now about the alignment. Because when you multiply 2 numbers, what's going to happen to the exponents? You add them. You add the exponents. So you don't have to align to match the exponents. Because you are adding the exponents. And then you multiply the fraction. So the alignment is not there now. Okay, so we relieved from the alignment. So because of that, now add the exponents when you do multiplication. If bias is used, subtract 127. Why? Okay, so why is that? If bias is used, we want to add the exponents, and then we want to subtract the 127. You double add, you double subtract, right? So this is the idea. Okay, so this is the idea. If bias is used, then you actually added it twice. So this one, if you remember, if this is the actual exponent, this is how it's represented if it is biased. And this is the other exponent.